Hi all, I'm here today with
Dominic.
as always, and we're joined by Professor Fountoulakis to discuss his paper Graph Attention Retrospective. And if you want to join the reading group sessions yourself, do so with the links in the description.
All right, so okay, so thanks a lot for the invitation. It seems that you have built a very nice lively community on Slack, so that's great, and we're glad for the invitation. So this is joint work with Amit Levy, who is at NOAA's art lab at Huawei, and Shenghao Asim are two of my students, and of course is also a supervisor of Asim. So the idea for the project started from a previous ICML paper that we have on graph convolution, and we basically use a similar data model that I'm going to discuss today. And basically the next step of graph convolution is to look at graph attention. And it's just when I looked at the graph attention mechanism, I had a light bulb moment, realized that there might be unfortunately something negative to say about graph attention. But as we were progressing, thinking about the project, there's also a lot of positive things to say. So so this talk is going to be about that. What can graph attention do well, and what it can do for specific data model, of course, on node classification. So can you see my screen? Did the slide change? Just verifying.
Yep.
Yeah. Okay. I'm in Greece, by the way, so I'm not 100% sure about how good the internet connection is. So if there's a problem, yeah, just let me know. Okay, so the first part of the talk is going to be very informal. It's just intuition about the results that we have. It's about 10 to 15 minutes, plus if you have any questions. And then the second part is just discussing details. The second part is also the part that is probably the roughest, because it's the first time I'm giving this talk. So if you have any questions, just stop me. This is timed for like 30 minutes or so, to 40 minutes. So there's, I guess there might be a lot of time if you want to stop me, you don't understand anything, something that you can ask. Okay, so we start with graphs. I guess everybody knows what the graph is. We have nodes, we have edges. But in addition to the graph, we also have features. So every node has its own feature vector, which is denoted here by xi. And the goal, the problem that we're interested in is the problem of node classification. So of course, given both the graph and the features. And some terminology. In this talk, I will keep using interchangeably things like same class edge and intra-class edge. Those are the same thing. And different class edge and inter-class edge, those are also the same thing. Same class edge is basically where you have an edge where both nodes of the edge are in the same class, and inter-class is the opposite. Okay, so the most popular graph neural network is graph convolution, and what graph? I'll just very briefly go over it. Maybe you know this already, most of you. So graph convolution, basically what it does is it does uniform averaging of features.
I think
so here we have node A.
Yeah. I also think we're good here and can go through this pretty.
Okay, good. So very quickly, right? It does uniform averaging. However, this slide probably I should stop a bit. When your goal is to do node classification, uniform averaging is potentially problematic because there are inter-edges. So you're going to have some transfer of information here from node D to node C. And again, when you want to do this kind of homogeneous node classification, then this might be problematic. Okay, so the graph attention was proposed to solve this problem. So graph attention is where you introduce this edge parameters gamma. And of course, for node classification specifically, the goal is to set the gamma for the edge C to D to an as small value as possible compared to the other gammas that are intra-class edges. So the goal of the paper is to ask that specific question: how successfully can graph attention drop edges, like drop inter-edges, and basically control the message passing mechanism of the graph neural network. More generally, we try to investigate how well can graph attention mechanisms discriminate neighbors. So to study that, we use a very simple data model, a toy synthetic data model, which is called the contextual stochastic block model. So this is a combination of a Gaussian mixture model and a stochastic block model. So here the adjacency matrix A is drawn from the stochastic block model, which has parameters P and Q. So in that model, we draw an intra-edge with probability P. So Aij is equal to 1 if I and J are in the same class. And we draw an inter-edge with probability Q. Here we're focusing on 2 classes. So for simplicity, you can analyze more classes as well if you want. So the adjacent matrix basically looks like a 2-block matrix. And then we have the Gaussian mixture for 2 classes where the features are generated using the normal distribution. For class C0, the mean is mu. And for class C1, the mean is minus mu. Again, the means can be general, but for simplicity, we chose here minus and minus mu. The variance is sigma squared. So variance is basically the noise here, right? And Q is also the noise for the graph. Okay, it's not changing slide. Okay, it does now. All right, so results, informally, based on the results that we have, we separate them into 2 regimes. We have the easy regime, which is when the distance between the means, which is mu, is bigger than sigma times square root log n. And we have the hard regime where the distance between the means is smaller than k times sigma, where k can be a constant or a non-constant. If it's a non-constant, it has to be up to square root log n. So the first result is for the when we don't use the graph. So I won't actually call that a result. This is based on classical observations, but we need it basically for context. You know, we need some benchmark to compare. So when we don't use the graph in the easy regime, the multi-layer perceptron can achieve perfect node classification. So now the question is, what happens to GAD? Let me turn this off. 1 second. Phone is ringing.
Okay, Amit, if you want to join the chat as well, we'd surely be happy to talk with you as well, I think.
Okay, I'm sorry, I'm back.
I just have a dog who's barking here, so I'll mute myself when he's like bark.
Okay, I mean, we have nothing against dogs here, I hope, but yeah. Now about the setup here a little bit. What is the, so am I getting it right? We have our two different classes or our 2 different features for our 2 different classes, but we sample them from 2 different Gaussians, and sometimes we have a larger distance between the Gaussians, sometimes we have a lower distance between the Gaussians, and
yes,
yeah, we hope that, well, if there's a large distance between the means, then it should be really easy for the model to distinguish the classes just based on the features. But also the nodes will play a little bit of a role, because if we only had nodes in one type of class, if we only had edges in one type of, if we only had intra edges, then yeah, it would be much easier to do the task than if we have also, like if we have a fully connected graph, for example, right?
Yeah. If I just the last part you said, I think so. Yeah. So let me repeat. So the distance between the means of the Gaussians is controls the noise, because you can think that if the distance is very small, then the distributions are going to overlap a lot, and then that's a problematic scenario. If the distance is large, but you have a lot of interedges, meaning that the parameter q is very high compared to p, then what happens is when you do, let's say, graph convolution, it's going to move the distributions also close to each other, and this will also create accuracy problems to existing models. So there are two types of noise. One is the distance between the means, and the other one is the inter-edge probability Q.
Yeah.
Right. So what we do is we study how the models are going to perform with respect to those two noise parameters, basically. Does it make sense?
Yeah, absolutely. I just want to make sure.
Yeah, no worries. So in the easy regime, you don't need the graph at all to perfectly classify the nodes. So how does the GAT perform in the GAT regime? Because in addition to the distance between the means, there is also a Q, right? So GAT is able, remember those gammas, which are the edge attention weights? Those are for the interedges, those are going to be significantly downweighted. So what does that mean in terms of node classification? For node, what you see in that plot is basically a theorem, which we'll discuss later on. In the x-axis, we have Q, which is the noise parameter for the graph. And the y-axis, we have the node classification accuracy. And you can see that here, the distance between the means has been chosen to be large enough such that we are in the easy regime. And here you can see that the GAT model achieves 100% accuracy for any Q, right? So basically the noise somehow GAT is able to completely filter out the noise that comes from the graph, which is Q, and is able to always perfectly classify the data. The MLP also doesn't use the graph at all, so Q here doesn't matter. You know, it's always a flat line. However, when you use GCN does uniform averaging, and if you remember from the previous slide, if you do uniform averaging, you cannot discriminate. So you're going to do some message passing between classes, and that's so if Q is very close to P here has been chosen to be 0.5, then performance of GCN starts to degrade a lot. So here you see the benefits of GAT actually. Does it make sense?
Yeah, basically we can say if we use the attention additionally, then we're sort of more robust, and more robust.
Yeah.
This type of noise, for example, where we have more edges.
Yeah, for this regime you don't need the graph, but if for some reason you use the graph because you don't know what's the level of noise in the data, it's guaranteed to be robust compared to GCN. And okay, so let's move to the hard regime. So for the MLP, again, no graph is used here. If K is non-constant, you're going to have at least one misclassified node. If K is constant, you're going to have a constant fraction of misclassified nodes. And now the big question is what happens to GAT? So for GAT, let's first talk about edge weights. So if K is non-constant, then at least one of the inter-edge gammas, they are not going to be downweighted. Sorry. And if K is constant, then those edge weights, the gammas, 90% of them, 90 here is chosen informally. We have the formal result in the paper. So 90% of gammas, they are going to be approximately uniform, where theta here means up to a constant uniform. So that probably reminds you GCN. GCN uses the uniform measure to do the averaging. So basically, GAT also doesn't offer discrimination in the hard regime where K is constant. And the question here is, does it matter? You know, maybe the data set is so noisy. If the distance of the means is smaller than K times sigma and K is a constant, maybe the data set is so noisy that you can't do anything anyway. However, this is not true. For that regime, node classification is possible. However, now it's going to depend on Q. So we're not going to have this nice plot anymore that we have on the right side. Node classification performance is going to depend on Q. The issue is that in order to convert this result on gammas to a node classification result, there we hit a technical wall from the high dimension probability tools that we could use. So the decision that we had to make basically is, do we wait 1 year or up to 40 years, 10 years? We weren't sure how long it's going to take, because we really had to improve existing. We had to improve something called Sudakov inequality, which we really couldn't predict how long that will take. So we decided to flash out the paper and leave this as a conjecture. So although we know that node classification for GAT is now going to depend on Q, we don't know exactly how it's going to depend on Q. And my prediction is that it's going to depend on Q in the same way that GCN depends on Q. And for that, we have this graph convolution paper at ICML where we know exactly how GCN depends on Q. Let me show you empirically what we observe on this synthetic data model. So this is the distance of the means has been chosen such that we are in the hard regime. So you can see in that plot that classification now, the node classification accuracy is a function of Q for all models. And so there is a region where GAT is actually worse than GCN. But if Q is very close to P, which is 0.5, then it seems that GAT performs better. Why? We don't know. And it's probably extremely difficult to capture that, that theoretically. Yeah.
For the MLP only mode, did you rerun the experiments every time, or like why is there? Are there?
Yeah. So these transparent areas around the lines, these are standard deviation. So we run. I think I ran 10 trials for each experiment.
Yeah. Okay. I just mean it should always be the same, right? Like on the Q does not change the no graph case.
Yeah, right. There was randomness from the features, though. Yeah.
Okay, but also in chat, like, do you know for the graph in the easy regime, or for the plot easy regime, how the experimental results go if you flip, like if you have more inter edges than intra edges?
So for the real data, we could not control how many. We could not control the noise. So we don't have a plot as a function of Q, let's say, for real data. But we did a lot of real data experiments without, yeah.
But this is real data, right?
This is not real data.
Yeah. So
I think he's asking about like general Q, right? Why here in the plot we see that Q is always less than P.
Yeah.
Right. So as like, and it should work for any Q. Like Q doesn't have to be in the easy regime. Q can be whatever you want, even like larger than P.
Was that the question?
like the question is just how, if we go with the Q further in this direction, how will the plot look? Do you know?
Oh, like beyond, if Q is larger than P?
Yes, exactly.
If Q is larger than P, then this is complete noise. Basically, what means you have way more inter-edges on expectation than intra-edges. So what will...
It should just
Doesn't
be
make sense.
50-50, no?
For it should be 50-50 for node classification for which model, GCN or GAT?
For GCN.
For GCN
And for,
yeah, it is close to 50% right now. But I guess it's what will happen is you're going to basically collapse everything to the same point. So any classifier is going to be is going to make 50%. Is going to have 50% misclassification, 0.5 misclassification fraction. Does it answer your question?
no. It's just a question from the chat. Like, why, if Q gets larger than P, then how does this graph continue? And like now,
oh yeah,
it's
going to be flat. Yes, you're right. Yeah, it's going to be flat at 0.5.
Okay. And
sorry, do you mind if I clarify? So
yeah.
The question was, does GAT eventually drop as we increase Q? So at the moment, GAT, even with 0.5, you still have 100%. And
yes, yeah, it's going to have 100%, even if Q is larger than P.
So it never drops. It stays at 100%.
It won't drop, and the reason that it won't drop is because you have such a strong signal from the features themselves that yeah, it's going to work. It's going to drop those inter-edges.
Okay, thanks.
perfect. Thanks.
Okay. So this is the last part of the. Oh no, sorry. Yeah. So this was basically all the results that we have in one slide. Let me start getting a little bit deeper. So what you see here is also a theory in the form of a plot. So here on the x-axis, we have the distance between the means. Y-axis, we have the gamma values. And you can see the purple line is the standard deviation. So on the left side of the purple line, we have the hard regime. On the right side, we have the easy regime. So you can see here for the hard regime that the average gammas concentrate around the uniform measure. And then as the distance between the means becomes larger, then larger than the standard deviation, then you start to see the separation between the intra and the inter gammas. In particular, the intra gammas remain large compared to the inter gammas where they converge to 0. For real data, we observe a very similar phenomenon. And yeah, so generally, let me put a disclaimer here since you mentioned real data. All the slides that I'm going to show here, they are mostly based on synthetic data, but in the paper, we did a lot of experiments on the real data as well. And we observed the nearly identical phenomenon there that as the ones that we present on synthetic data. So if you want to see a lot of real data experiments, you can just look at the paper. And yeah, any questions about that, or are we good about the plot?
Not about the plot, but the GATs that you're usually using here in all of your experiments. Is it the standard GAT of Petter,
yeah,
or is it GAT V2?
That's a good question. So this is not the standard GAT. It's actually a more powerful attention mechanism than the original GAT. But in the detailed section of the presentation, we'll see that the results that we are talking about also apply to the original GAT, and we'll also show experiments on the original GAT as well. The MLP GAT is basically, I will define it specifically in the detailed section, in the detailed part. The MLP GAT, basically just satisfy your curiosity, is basically a two-layer attention mechanism versus a one-layer attention mechanism that the original GAT has. Does it make sense?
And yeah, but it's not the type of attention that we're using in GAT-V2, but it is still dynamic. It is still dynamic because we have the non-linearity in between, right?
It is basically a generalized version of GAT-V2, Okay, so why does GAT fail to discriminate? And the reason that it fails, if it's going to fail, of course, is because the attention mechanism basically represents edges as the concatenation of the features of the nodes that participate on that edge. So if you have here edge AB, the nodes A and B, then the edge is represented by the concatenation XA, XB. And then gamma, how it's usually set, is basically parameterized using an MLP, which takes the concatenation as input. So now you're already probably thinking, if I can make the MLP to separate, in order to make that MLP to separate intra from inter edges, then I need to have some structure in the concatenated vectors. And in fact, that's the case. Since XA and XB are themselves Gaussian vectors, then the concatenation is also a Gaussian vector. And in fact, the structure of the data looks exactly like the XOR problem. In case you're familiar with it, if you're not familiar with it, it just looks like the figure that I have here. Right. So what we're trying to do here is our goal of the attention, if it wants to be successful, is to separate the blue from the red. And if the distance between the means, which is the norm of mu, is bigger than sigma squared log n, meaning that we are working in the easy regime, then this is possible. However, if the distance between the means becomes small, comparable to the standard deviation, then the distributions basically collapse, and then it's nearly impossible to, at least with high probability, to successfully separate intra from inter edges. So that's basically the gist of why attention might fail. Okay, so let me conclude, a brief conclusion, then we'll go in the detail part. So attention is able to discriminate. Unfortunately, this is going to be successful only when we actually don't need the graph. However, there is advantages to using GAT because of robustness that Hannes mentioned. And the reason that it fails is because, again, because of the representation of the edges as the concatenated vectors. The concatenated vectors have the property that they become noisy way faster than convolution fails to classify the data, right? So what does that mean? It means that even if attention fails, we can still have node classification, right? So that shouldn't happen, right? Ideally, you would like to have the attention mechanism to work whenever you have node classification as well. So yeah, for real data, again, I've personally done a lot of experiments, and I put a lot of pages of experiments in the paper. So for real data, we observe similar trends as for the toy synthetic data model that I presented. And yeah, so that brings me to the second part. If there are any questions, otherwise I should continue probably. Are we good?
Let's dive into details.
Okay, good. So assumptions. We have two assumptions. The first is for the intra-class edge probability. We require it to be at least log square n over n. N is the number of nodes. The inter-class edge probability Q also has to be at least log square n over n. And we also require P to be larger than Q, although the friend who asked the question about P and Q, you don't really need that P and Q for GAT to drop edges in the easy regime, but we have it here because for the node classification problem, basically to make sense. Yeah, so what does those assumptions mean? They basically mean that the expected number of neighbors for every node is at least log square n. Okay, so GAT convolution. Here's how it looks like in case you're not familiar with the exact expression. Node I aggregates informations from neighbors j, and it also puts a weight gamma ij to each neighbor. And the gamma ij is basically a softmax, which is applied to a classifier psi. And the psi takes as input the combination of edge features from nodes I and j, and it's usually an MLP. So that's the GAT convolution that we are interested in. Let's start with the first result. Classification of edges in the easy regime. So let me read the theorem. So let's suppose that we are in the easy regime, meaning that the distance between the means, which is the norm of mu, is bigger than sigma squared log n. Then we can find an attention architecture psi such that with probability very close to 1, we can separate intra from inter edges if the data have been generated from the contextual stochastic block model distribution. This is the theorem in the form of a plot. So as a function of Q, you can see that the MLP GAT is able to achieve perfect node classification. And I will define the MLP GAT in the next slide. So that's basically what the theorem is saying here. You can perfectly separate intra from inter edges. Yeah.
Can you go a slide back?
Sorry, say it again.
Can you go a slide back? What does
slide back, yeah.
The little omega mean? Like I know what's little o.
Oh,
little.
Yeah, little omega means a strictly larger order than what's in the, yeah. Big omega could be of the same order. Little omega means strictly bigger order.
I don't know. For some reason, I was thinking this was a small theta. Yeah. And
Okay.
theta doesn't make sense, right?
Should I continue?
Yeah.
Okay, so here's how we prove that. Again, our goal is to find an architecture size such that we can solve the XOR problem, meaning separating the blue from the red. And we can reduce this problem to finding architecture psi that is able to set the sign of the upper left quadrant and the upper right quadrant and the lower left quadrant to be positive, and the other quadrants they have to be negative. And the reason that this is successful is because the distributions, because the distance between the distributions is so big, and compared to the variance, compared to the standard deviation, then basically the whole distribution is within the quadrant with high probability. So if you have a psi function with the right signs for each quadrant, then you basically perfectly classify the edges as well. We can actually construct such a psi function. It's going to be, like you said, a two-layer MLP. And yeah, the way that we pick the psi function is by, we ask from it to, we look at correlation. we measure correlation. The psi function is basically measuring correlation with the means of the XOR problem. So if you are if you are an interedge, you should be correlated with the mean of interedges. If you are an intraedge, you should be correlated with the mean of one of the means of intraedges. And yeah, so that's how we prove this result. So okay, so gamma. So we need something stronger than just classification of inter and intraedges. We need to know what's the exact value of gammas, because gammas are going to be part of the gut convolution. So this result is that. So if the distance between the means is bigger than sigma square root log n, then if we use the psi function from the previous slide, we can show that with probability 1, the gammas for the intraedges is going to be 2 over np, and the gammas for the interedges is going to be way smaller. Little o here means smaller order than 1 over n times p plus q. So we have a very nice separation of the intra and inter gammas as well. Here's what the theorem in the form of a plot again. So you can see here that the intra gammas, which is denoted by the blue star line, basically overlaps with 2 over np, which is what we prove in the theory. And then the inter gammas are very small. They concentrate around 0, and the black line is basically the uniform measure, which corresponds to GCN. Okay, I'm continuing. So how do we prove that? We need to understand how the psi function works, and we can show that with high probability, the psi function is going to be very large positive for the intra edges and very small negative, sorry, and very negative for the inter edges. And in particular, for the intra edges, the value of psi is going to concentrate around 2 times r times the distance of the means, the norm of nu, times 1 minus beta, where beta is the Lee-Hirel parameter. R is a parameter that we control in the psi function. And so you can see here that the margin of classification is very large because you have something large positive and something large negative. So we're going to exploit that in order to say something about gammas. So all we have to do here is just plug in those concentrations into gamma and then see what happens. So here's an example for an intra-class edge. So the numerator is going to be e to the 2 times r times the distance of the means. And the denominator, we're going to separate it into intra and inter edges. And you can see that the exponent for the inter edges is very large negative. So this basically is 0. So all you're left with is intra edges, right? And then using some concentration properties of the graph itself, we can show that with high probability, this gamma is going to be 2 over np. So what I'm hiding here is high dimensional probability tools that I don't think we should discuss those ones. If you have questions, let me know. And here's an example of an inter-class edge. Here the exponent is large negative. The denominator in the exponent in the numerator, the denominator is the same. So because the exponent in the numerator is so large negative, the whole thing becomes very small, much smaller than the uniform measure. So this is going to be little o 1 over ni, where ni is the number of neighbors. Yeah, so that's how we prove this result. And so
can
okay.
I ask a question?
Yeah,
So,
of course.
on the previous slide, can you give us an intuition about why do you need this 2 in the numerator? Because I think that's what's requiring you the log square.
Yeah. Yeah. So the number of intra neighbors is the expected number of intra neighbors is n over 2 times p. So it's a bit unfortunate I cannot write here. So let me repeat the same a little bit better. If we remove this part, the inter-edge part, right, then you are left with the numerator and the intra part of the denominator, right?
Yeah.
But those two things are the same, so we can just remove them completely, right? So you basically have here 1 over the number of intra-edges, right?
I see. Okay.
So how many intra-edges do you have? N over 2 times p on expectation. And that's how you get the 2 there.
Okay. Yeah. So, but why do you? So why do you need it? Do you need it in the theorem? I mean,
it's not. No, it's not really important. I guess your question has to do with the next slide. Does this two make a difference in the node classification result? No, it doesn't.
Okay.
I just was a bit precise, unnecessarily precise there, I guess. Yeah, it's not needed there. So node classification. So how do we use those gammas now in order to prove something about the nodes? Again, in the easy regime, if we use that constructed psi architecture, attention architecture, with probability very close to 1, we can show that GAT is able to perfectly classify the nodes for any P and Q. So it's the same plot as in the informal part. So now I guess I shouldn't go over it again. It shows exactly that there exists a GAT architecture which for any Q, at least here what is shown up to P, is going to perfectly classify the data. GCN can't. All right, so how do we prove this? Well, we have to utilize the gammas from the previous theorem. So what we do is we take those gammas, there's a large gap between intra-gammas and inter-gammas, and we plug them into the convolution equation. So after you plug them in, you get that the inter-edge part of the convolution operation is basically 0. So all you're left with is the intra-edge part of the convolution. And this, in combination with this, results actually in a very nice variance reduction. So meaning that the variance from sigma is now going to become sigma over square root times NP. So this is way smaller. And at the same time, the distance between the means is very large. It's little omega sigma square root log n. So if you have a distribution where a Gaussian distribution, or roughly Gaussian distribution, where the means are far apart and the variance is way smaller than the standard deviation is way smaller than the distance of the means, then you have very nicely separated data, and that's how GAT achieves perfect node classification, independent of what Q is. Okay, so that's all about the easy regime. Now we go into the hard regime. Okay, so here things become a little bit more complicated. So the hard regime means that the distance between the means, which is the norm of mu, is k times sigma, where k is some. Yeah.
Can we have a question?
Yeah.
Hi. For your attention mechanism in the easy regime, like what?
This one.
Yeah, I don't know. Oh, is this so this is the whole attention mechanism? Like this is all the parameters you use basically?
Yeah.
Okay, so like the width is like very small.
The width is very small. What do you mean by the width?
Just like the number of parameters.
Oh yeah, it's enough, right? Because you basically have everything basically is the XOR problem, right? You have basically 4 means. So as I'm saying here, you need to measure correlation with the means, but you only have 4 means. The reason that you only have 4 means is because I started with 2 classes only. If you have more classes, then you have way more means, and then you're going to need more parameters as well.
Okay. And in your experiments, are you training the GATs?
I do both. So in the main paper, I use this constructed attention, but in the appendix, we also have a large section where we repeat all the experiments, but with training. And yeah, as I said, we observe very similar trends there as well.
Okay, cool.
Okay.
Thanks.
Yeah. Okay, so hard regime. Distance is at most k times sigma. And so we have 2 parts here. The first part assumes that k makes sense. The first part makes sense where k is a constant. So if k is a constant, then with probability close to 1, we're going to misclassify. The fraction of misclassification is going to be what I have here, which is 2 times phi complement k squared. Now I will explain better this function in the next slide. For now, let me just say that phi complement is basically 1 minus the cumulative density of standard normal. And again, I will explain this misclassification fraction better in the next slide. Let me go to the second part for now. That has some interesting twist. So in the second part, if k is not a constant, then we can only, at least our results, for our results, we can only claim something for when q is something slightly bigger, right? So previously we assumed q to be at least log square n over n. Now we have something bigger, and if we have such a large q, then we can claim that psi is going to misclassify at least 1 integer with high probability. Okay, so we have 2 parts, right? In the first part, when k is constant, we have constant fraction of misclassification. The question is how much, and that's going to be shown in the next slide. And the second part is that if you have a slightly noisier graph, but k is non-constant, then we still have at least 1 misclassification for the edges. There's a gap here in sparsity compared to what we started with, but yeah, so that's the best we can do. Not in general, that's the best we can do, meaning the people who wrote this paper. So yeah, so if beyond that q, we don't know what happens. It might fail, it might succeed. We don't have a result for that. And so let me talk about the misclassification fraction. So here on the y-axis we have the misclassification fraction, and you can see how it changes as a function of k. So in order to have a large misclassification fraction, at least for the synthetic data model that we work with, you need to have k to be something like 0.25 or something like that. So if k is even around 3, you have a very small misclassification fraction. Okay, so that k matters. Here is the theorem in the form of a plot again. You can see here that we have close to 60% classification accuracy for intra and inter edges for as a function of q. Okay, so all right, so all the discussion so far was about some general attention mechanisms. Oh, by the way, I forgot to mention, the negative regime is for any attention mechanism. It's not only for the psi, the specific psi function that I showed earlier in the easy regime. This result is for any attention mechanism psi. But okay, so what can we say about the original GAT mechanism? So here, if sigma, the standard deviation, is a constant, and if the learning parameters of the model are also a constant, Here we can show that with probability very close to 1, at least 90%, the 90% again is slightly arbitrary. We have the details in the main paper. At least 90% of the edges of the gamma ij, sorry, they're going to be approximately uniform. Right. So the result that I had initially in the informal discussion was basically referring to the original GAT. So let's see that result in the form of a plot. So here I visualize both the MLP GAT and the original GAT for two heads, and you can see that pretty much all the gammas for all models, they concentrate around the uniform measure, which means that there's basically no discrimination, since that is very similar to GCN. And how do we prove that? Well, it's same phenomenon as before. I've mentioned a lot of times. The distributions collapse because the distance between the means is comparable to the standard deviation. So when the distributions collapse, then the data basically act like Gaussian noise. So we cannot extract any useful information from the data. So this, in combination with some technical results, which about standard normals. Also, for example, for standard normals, we can say that if we draw a lot of standard normals, right, a lot of those standard normals are going to have constant magnitude. There's going to be with high probability some would have large magnitude, but a large fraction of those are going to have constant magnitude, and that's where the 90% is coming from as well. So using this property, we can claim that size are basically going to be a large fraction of the size are going to be constant magnitude, and this implies that gamma is approximately uniform. This is technical again. The gist of it is again that we have distribution collapse, and we can extract useful information from the data, and that's why we get the uniform measure for the gammas. Okay, so as I mentioned at the beginning, all the results for the hard regime for GAT, we only talk about the edges. We don't have a node classification result, but here is the conjecture, is that the question is, how does node classification for GAT performs as a function of Q in the hard regime? And my conjecture is that it performs, the dependence on Q is the same as that of GCN. And here I'm showing you that exactly that. So if P minus Q is of the order of sigma square root log n over the expected degree, then we're going to fail to perfectly classify the data. So this is basically GCN territory. Again, here's that plot that shows that both GAT and GCN, the node classification performance depends on Q. We saw that before. Okay. I don't know, any questions? I have two slides more and then I'm done, I guess. If you have any question, maybe before I talk about how we can potentially fix that.
Not from my
No?
side.
Okay, no worries. All right, so can we fix that? Yes. Is the solution a good solution? I wouldn't claim that, and I will explain in those two slides. So the way that we solve this is the way that we solve the attention issue is by first convolving the data before we give them as input to the attention mechanism. Because the current attention mechanisms, they take the input features, the original input features as input to the psi function. If you first convolve before you give them to the attention mechanism, then you can actually prove that you can improve the threshold of edge separability to sigma square root log n over square root n times p plus q from sigma square root log n. This is a huge improvement. It's actually very easy to prove based on the previous paper that we have. It will probably take us one day to write this down. However, because now we are using GCN to improve GAT, the dependence of GAT is also going to depend on Q. And I have the same conjecture here. But by the way, this discussion is not part of the paper, right? So I just thought it's going to be nice to mention. And my conjecture here is again that even if you use that improved GAT mechanism that I mentioned just now, I believe that in terms of node classification, you're not really going to see an improvement as a function of Q. So that leads us to a negative message, because basically I'm telling you that I don't know how to beat GCN, at least for this particular data model that we are working with. And to be honest, for this particular model, I also don't believe that GAT is better than GCN. But that's my conjecture. And yeah, so that leads me to the end of the talk, and thank you very much for your attention.
Thank you for the awesome presentation and all the answers to our questions. Are there any more?
What happens with problems where Q is specifically larger than P? So something like graph coloring or something that's related at least to wanting to have nodes that are not related to their neighbors.
Yeah, we asked that earlier. If Q is larger than P, then in the easy regime, GAT will still be able to drop those inter-edges. In the hard regime, though, you're going to get complete noise.
Sorry, I meant in terms of fixes, whether you might have some fixes for this regime.
For the hard regime, so yeah, I mentioned at the beginning that I don't know how to fix this specific setting. I think if you really want the attention mechanism to be successful, is you probably need to have different types of features for edges. If you have, because how can I say this? Anytime that you want to improve something, right? Not anytime. So usually when you want to improve something, you need to have some extra piece of signal like that. That is you can utilize. Having features for edges, I think, is going to be an extra signal, an extra piece of information that you will be able to utilize in order to do edge attention properly. Just using the axes, the node features, again, I'm a bit negative if you can be successful in the hard regime. Yeah, so I don't know if that answers exactly your question, or maybe opens up more questions. Or just
No, I mean,
guess
it definitely points to some directions of considering edge features. Yeah.
More questions is great as well.
The way that I think of this is that in the previous paper in the ICML paper, the GCN paper, we show that if you use the graph in addition to the features, then the signal that comes from the graph basically enhances classification properties of the models, right? So that's why I mentioned, I believe that in order to basically solve this problem, you will need one extra piece of information, and that's probably edge features.
So do you have some opinions on how well GATs are able to generalize compared to GCN?
So all the results that I mentioned about separability, they all are generalization results. So it's not only about training, it's also, the results also are about generalization, at least for the particular distributions that we are working with.
Yeah.
Now, I guess you're talking in general, like for any sort of distribution, or
Yeah.
I think there have been results by the group of Gegelka on general distributions where they basically use the pack learning framework. These are worst case results. So if you want to basically classify what type of results you can get, you can have pack learning, which does not assume anything about the distribution. The negative thing is that they are not very tight. And then you have the other type of results using specific data models that we are using here, where you can get extremely tight results. But again, you lose the generality of the bounds of the complexities that we are getting.
Okay, but I don't understand why you say it. You're talking about generalization. Like, if you're just saying there exists an attention distribution.
Yeah.
There exists an attention distribution that is able to. Yeah, of course, then if we have that attention distribution, then we are able to distinguish the classes. But
yeah,
generalization, there we talk about learning, it's right, and then seeing if we can generalize.
Yeah,
not setting our weights
for
in a particular way that we would need it.
Yeah, for the particular distributions that we are working with, you can train, and then you can generate more data, right? And then you can ask your question, generate more data from the same distribution, and then you can ask the question, will the trained function work well on the new data? That also, but they are new, but they come from the same distribution, right? That's same distribution. Yeah.
Is that actually the case that you will always find this? Yeah.
Oh, okay. So you're not asking about generalization. You're asking about how to, if we can prove the same results for when we use learning paradigms like the ERM, for example, right? Yes. So no, we haven't studied that. So what you want to study is if gradient descent, for example, is able to recover good parameters that generalize, right? So we haven't studied that in the paper. All we show is that there exist parameters.
Asking, if you have some thoughts or opinions.
I have an opinion. The opinion is the following. Unless you do random feature models, like this double descent stuff, if you have heard, then it's going to be extremely difficult to analyze what you're asking for. The reason that it's going to be extremely difficult is because you are giving us input you're giving Gaussian input to highly nonlinear functions. And then it's very technically difficult to work with such quantities. But there is the alternative again, of course, of doing this random feature models by the group of Montanari, where they basically study exactly what you mentioned. They show that gradient descent, for example, is going to converge to a good set of parameters. But again, the architecture that they are using is not the standard architecture that practitioners are using. So there's that gap there. So I haven't tried exactly what you asked for. I believe it's going to be difficult, technically difficult. You can make it easy though, if you use techniques like the neural tangent kernels and random features and things like that, theory people have been using.
Okay. Well, anyway, thanks again for the nice insights, and also thanks Amit for joining in as well and answering questions in the chat as well. But are there any last words you want to want to make?
No, I don't know. That's it. You mean in terms of the paper or?
Whatever you want.
Yeah.
But no, that's fine as well. And then I can just say, yeah, thanks and have a nice evening, I suppose. Ideal.
Yeah.
Okay, now we know a lot more about what graph attention networks can learn or not learn, at least about stochastic block models, but hopefully we can extrapolate those results somehow. And if you want to have interesting discussions like this in the future yourself, ask your questions, join us in the Slack channel or join the mailing list. And in the Slack channel, you'll find people like Professor Fountoulakis and other professors you can chat with. And you'll get notifications for the upcoming papers, can vote for other papers. See you.